In this video, we'll be discussing how to determine the amount of medication in a specific amount of solution. That information will be on pages 560 to 561 in Chapter 22. When we talk about medications in solution, so you have your bag of IV solution that can be anywhere from 50 mLs to 1,000 mLs, and you are injecting the medication into that bag. The order that you'll see may be for a certain amount of medication to be given over a certain period of time, but you're not going to work this problem like you do the piggyback IVs. It's going to be different. So let's take a look at this order that you would see for this one. The order might say something like 15 milliequivalents of potassium chloride in 1,000 mLs of D5NS to be administered at a rate of 2 milliequivalents per hour. So one thing to clue in on is that your potassium chloride is given, or should always be given, by a pump. Pumps are programmed in milliliters per hour, and you're not given any type of drop factor for this, so you can't calculate drops per minute. So when you're trying to calculate the amount of solution, okay, that is milliliters. You need to program this pump in milliliters per hour. So you have to figure out how many milliliters per hour to infuse in order for that patient to get these 2 milliequivalents per hour. So let's take a look at how to do that. Just to show you what your problem might look like, you might not have any words. So here's your order that you're going to give potassium chloride 20 MEQs in 1,000 milliliters of normal saline, and you're to program the pump to deliver 2 MEQs per hour. So again, I need to figure out how many milliliters per hour to program this pump, because that's how we program pumps. And this is what your bag of solution would look like. Remember, I told you sometimes these medications come from the manufacturer already in the bag of solution. So this bag of solution tells you there's already 20 milliequivalents of potassium in 1,000 milliliters. And this one's actually 0.45 sodium chloride, but just pretend that it says 9%. Again, we are going to be calculating milliliters per hour. We were not given a drop factor. This is being given by IV pump, and we program pumps in milliliters per hour. Our first equation or fraction needs to have milliliters in the numerator. This right here says milliliters, so that is 1,000 milliliters. The 20 milliequivalents is what is related to that 1,000 milliliters, so we'll put that on the bottom or the denominator. That means our next fraction must have milliequivalents in the numerator. And we are told 2 milliequivalents per hour. 2 milliequivalents per 1 hour. Now we don't have any information left, but let's just double check ourselves to make sure we didn't miss anything. We have milliequivalents here, milliequivalents there, hour, and milliliters, which is good because we're looking for milliliters per hour, so we are set up correctly. 1,000 times 2 is 2,000. 20 times 1 is 20. 2,000 divided by 20 is 100. And your label is milliliters per hour. You can also solve this equation using ratio and proportion. So you can take your known, which is the 20 milliequivalents in 1,000 mLs, and then milliequivalents must be in the first position on this side. So I know that I have 2 milliequivalents, and I need to know how many mLs that's in. It's going to be X mLs. We're going to do means and extremes, or innies and outies. You've got 2,000 is equal to 20x. You need to get x by itself, so you divide by what is next to x. What you do to one side, you must do to the other side. X is equal to 100, and don't forget your label, which is milliliters per hour. Let's take a look at this case study. Mr. Flint's lab work is back and his potassium level is slightly decreased at 3.1 milliequivalents per liter. The physician changes the IV fluid to 1 liter of D5NS plus 20 MEQs of KCl at a rate of 2.25 MEQs per hour. Now again, even if you didn't realize that potassium generally gets run on a pump, you have no drop factor given here. If you have no drop factor given, you cannot give an answer in drops. Your answer must be in milliliters per hour. Our first fraction needs to have milliliters in the numerator, so let's look at the information we're given. We're given liters, 1 liter, and it has 20 MEQs of KCl. Now I can just convert that 1 liter to 1,000 milliliters in my head, which is the easier way to do it. But in case you don't remember that, you can always just calculate, put your conversion factor in here. 1,000 milliliters is 1 liter, which if you remember the conversion factor, you can just write it in. But just to show you another fraction in here. Then your next fraction must have a liter in the numerator. 1 liter contains that 20 MEQs of KCl, which means my next fraction must have MEQs in the numerator. And our other piece of information has 2.25 MEQs per hour. And let's pause and take a look. I have a milliliter here and I have an hour there. I should be set up correctly, so let's double check. My milli equivalence repeats, my liter repeats. I'm left with hours and milliliters, so we should be set up correctly. 1,000 times 2.25 is 2,250. 1 times 20 times 1 is 20. 2,250 divided by 20 is 112.5. When you are using a pump, unless I tell you otherwise, you need to round to a whole number. For pediatric IVs, heparin IVs, I will tell you to round to the nearest tenth, but that is nowhere in these directions. So you must round to a whole number. Here's the tenth position. This is 5 or greater, so you need to round up, which means our answer is 113. There's your label, milliliters per hour. Let's look at how to solve this using ratio and proportion. Mr. Flint's lab work is back and his potassium level is slightly decreased at 3.1 milliequivalents per liter. The normal range is 3.5 to 5.0. The physician changes the IV fluid to 1 liter of D5NS plus 20 MEQs of KCl at a rate of 2.25 MEQs per hour. We need to find our known for ratio and proportion. Our known is that we have 1 liter of D5NS with 20 MEQs of KCl in it. Now our answer needs to be in milliliters per hour. So personally, I would just change this right away to 1,000 milliliters. You want to convert it. And then I would write 1,000 milliliters is to 20 milliequivalents as, we don't know how many milliliters because the only other information I have here is the MEQs per hour. So I need to write X milliliters is to that 2.25 milliequivalents. For ratio and proportion, you're going to do your means and extremes or innies and outies. You have 1,000 times 2.25 gives you 2,250. 20 times x is 20x. You need to divide by what is next to x to get x by itself. What you do to one side of the equation, you must do to the other to keep it equal. X is equal to 112.5. Remember I told you for a medication pump, unless I tell you otherwise, you are to round to a whole number. Sometimes you'll see me put in the directions to round to the nearest tenth. You'll see it for things like heparin, peds IVs, things like that. But in this case, that is nowhere in the instructions, so you must round to a whole number, which means your answer will be 113 milliliters per hour.